Greetings and welcome, friends. Happy mathematicians. It's great to be back. In case the internet didn't know, I was away for like a week, and I know everyone was on pins and needles waiting for my next video to come out. And here it is. You're enjoying it right now. Of course you're enjoying it. It's the best video you've ever seen in your life. So here it says, use residuals to determine whether the model is a good fit for the data in the table. So here they gave us an equation, and they gave us a table, and they basically want us to know, does it fit the data, right? How well does it fit the data? And I happen to have this data already set up in a little Google Sheet. I found page 206, number 5. Is this the right one? Am I on the right problem? I don't even know. No, I'm on number 7. So watch this, how fast I can solve this problem. Bing. There's number 7. Gorgeous. All right, so let's write our predicted value here. According to their model, all right, here we go. Y equals negative 1.3x plus 1. So what I'm going to do is plug in all of these x values and figure out what the predicted y value would have been. Negative 1.3x plus 1. And so I'm going to write in equal sign, because this is an equation, negative 1.3 multiplicado, my x is this value over here, and then plus 1. And what this does is it plugs in negative 8 for x in that little equation, and it tells me what it's equal to, which is apparently 11.4. Let's do one of those by hand, just in case. I'll just call this predicted y. So if I had y equals negative 1.3 times negative 8 plus 1, that's a calculator problem in my book. 1.3 times 8. Man, I'm so good at singing. 11.4 is what I got. So the predicted y was 11.4. Is that what we got on my spreadsheet? Better believe it is. And since this is a spreadsheet, this was the pro tip that I taught you. If I move my cursor over this square here down at the bottom right, click and drag all the way down, that actually then will take this x value and plug it into that equation, or this x value and plug it into the equation. So here are all of the predicted values, all right? And now what I'm going to do is find the residual, all right? Residual. And the residual, what we would do is we took the actual and subtracted the predicted, or was it predicted minus the actual? Do you guys remember? It's been a long vacation. Technically, my interpretation won't change any if I do it the other way around. Also, I realized I'm editing the master copy of this. Well, I'll have to revert later on. Well, let's see. Well, one way I could find out. Predicted. Let's see. This is the sort of quality stuff you get. All right, you take the data point. Yeah, data point minus the predicted. There we go. So if I want to calculate that here, I'm going to take the data point and subtract its corresponding predicted value, and I get a residual of negative 2.4. Let's drag that down. Gorgeous. There's my residuals. Well, not really, other than they were the difference between the predicted values and the actual data values. So my pattern, I guess, was that they were the outputs of this formula subtracted from the actual data values. So if I want to see if these are good or not, this is one of the ways we did that. We would select the x values and then hold control and select these residuals, and then we were able to insert a chart, right? You guys remember that? And we, nah, that's not the prettiest. Let's scroll down to scatter. All right, and look at this. Here's a beautiful chart. Gorgeous. And notice I've got about half of the points. I've got 1, 2, 3, 4, 5 above, 1, 2, 3, 4 below. They seem to be kind of right every other-ish. And so I would say this is a pretty good model, right? It's pretty good. Those residuals ain't far off. The other way we were able to do this, do you guys remember? If I copy my data points, Cameron, and go to Desmos Calculator, and I plug those in here. Notice here's my data points, right? You guys remember that? Desmos, or a graphing calculator, was actually able to find these residual values for us. What we did was y1 tilde mx1 plus b, and then it would actually find, right, the best fit equation that represented that. Notice their equation is not the same as the one that they gave us here. Pretty close though. Yeah, pretty darn close. And here's, it says residuals. If I hit plot, actually I'm not in projector mode. There we go. Now you can see that. And if I hit plot residuals, these black points are all of the residuals. And you can see that some of them are a little bit further off. They're a little farther from the x-axis, right? So the line wasn't a great fit for this right here, right? Wasn't a great fit. Our predicted value was 3.6. The actual value was 8. So that's quite a ways off. But it does appear to have somewhat of a linear trend. Question, comment? No? All right. The other thing that we were able to do was, I think we were able to actually type in our model where we could say, how was it? I think if I just do negative 1.3 times x1 plus 1, right? If I wanted to actually use their equation instead of the best fit one, right, we could do that. I think I was even able to call this something like f of x equals. Was I? No. No, that's too bad. So those are the predicted values, but I could then do something like this, do y1 minus those predicted values, which I wish I had a shorthand way. There's got to be a way to do it, but I'll just put it in parentheses, negative 1.3 x1 plus 1. And if I subtract those, these are the residuals. Notice those numbers should look familiar to us. Negative 2.4, 1.2, negative 1.2. Yeah, those are the same ones that I have here. Oop. And these residuals, what color are they? Blue? Are they the blue ones? Yeah. The blue ones are the residuals based on their model. Let's actually hide these ones. Yeah, they're so close, you can't even tell. They're off by very, very little. All right, but that was the idea of how residuals worked. You were kind of trying to look for the same number above as there was below. All right, all right. So I'm going to say it's a pretty good model. It is a pretty good model. I said predicted Y, pretty, what I called it. You can do these by hand, by the way, where you actually plug in all of your X values, and then you'd subtract. Yeah, it takes a while, but it's a pretty good model. It had the same residuals, had same amount above or below. Right? So, it's a pretty good fit. Pretty good fit. Let's keep cruising. There's more interesting problems here. We'll come back. Don't you fret. Use a graphing calculator. You guys didn't have graphing calculators, but you could have used Desmos, or you could have used Google Sheets. You also could have used Excel if for some reason you had a copy of Excel laying around. Find the equation of the best fit line. This is number 11. So let's see. Here's number 11. I'm going to use Desmos for this one. I'm going to copy this data. I'll open a new Desmos. Gentlemen, you with me? I need you with me. Thank you. Cameron, thank you. So here's that data from question 11 plotted. It looks like a linear equation will represent that pretty well. Let's find what the best fit equation is. I'm not in projector mode again. Bam. There we go. So I'm going to do y1 tilde mx1 plus b. Notice that. That seems to be predicting that pretty well. And then I could make extrapolated predictions where I could go beyond where my original data set was. Interpolation was when I predict a value in between, Cameron. And extrapolation would also be before. So if I'm going outside of what my original data said, it's called extrapolation. So let's find these residuals. Oh, actually, wait. This problem didn't even ask me for that. They said identify and interpret the correlation coefficient. Does anyone remember what that was? The correlation coefficient was this R value. All right. So this is what we're interested in. There we go. That's the R value. Let's see. They actually wanted the equation of the line of best fit. What would my equation be? What is the equation of this purple line? Does anyone know how to interpret this? It'd be y equals m. What's my m? I just blocked it on us. M is equal to what? Yeah, 2.07x. Yep, 2.07 times x plus b. Yeah, let's call that minus. I like that. 7.5. So here is the best fit equation that represents this data. That means the slope is going up by about 2.07 each time, and that the y-intercept was negative 7.5. So what do these mean? You guys remember? So this R value is called the correlation coefficient. R is a number that is between -1 and 1. The closer it is to 1 or -1 means the better this equation is at representing the data. So I like to think about this 98. I like to pretend it means like 98% accurate. Although that's like a super loose kind of understanding of what that means. Also, because the R value is positive, right, means that it is a positive correlation. That means as my X increased, my Y increased. The other way I could have figured that out regarding the positive correlation is, all right, right here tells me positive correlation. Also, because the slope is positive, it's telling me the same thing, that it's positive. All right, so the number is kind of like how accurate it is. So if this was like 0.8 or 0.5 or 0.3, that means my model would less fit the data, that the data would have been further from my line. But that it seemed to fit pretty okay, All right, let's keep going. Oh, 19, here we go, awesome. All right, here's a table that represents the mileage in thousands of miles and the selling prices in thousands of dollars of several used automobiles. I've been looking for a car myself, but I'm not desperate, so I'm going to wait until a good deal shows up. It says, use a graphing calculator to interpret the line of best fit. So, this was question 19. Bam, question 19 in the Google Sheet. Here's the data. I'm going to do this using Desmos. I'm really a fan of Desmos these days. You guys liking Desmos? Put mine in projector mode. Let's paste this data. Here we go. So here are the values of cars. Let's see. The mileage is X. I wonder, can I label that? Add a label, X. Mileage. And the Y is price. Price. Bam, look at that. I can even throw some little labels on my axes there. That auto scale for us. It's always available to see. Okay, so it appears as though the fewer miles a car has, that the cost is higher or lower. If it has less miles, higher, or if we set it a way that makes more sense, the more miles on a car, yeah, then you can see that the cost seems to be going down. It seems to be lower. So let's do the Y1 tilde M X1 plus B. There's our equation. All right, let's take a snapshot of that. Oh, was it a perfect hit? Oh, no, not quite. It's close. Yeah, the further out I go, the more closely it'll appear, but yeah. Okay. So, it says identify and interpret the correlation coefficient. So, what is the correlation coefficient? This is the correlation coefficient. It's negative. That means it's a negative correlation. Right? That As mileage increases, the price goes down, right? That down is the negative that we're talking about. And also because it's 0.96, it's a good model, right? It's strongly correlated. There's a strong correlation. I could say that. Right? And we can pretend that's like a 96% accuracy. Even though that doesn't fully make sense because, as we pointed out, the points actually aren't exactly on the line. None of them are, right? Cameron, you guys with me? All right. So let's see. This problem gets a little bit more interesting. It says interpret the slope in y-intercept. So the slope is negative 1.836. The y-intercept was 19.7. I'll round that up to 2. Okay. So what does this mean? Now, slope is rise over run. And in my graph, rise is the price over the run being in mileage. So if the slope is negative, that means it is decreasing. All right, decreases 1.836 thousand dollars. Sorry. So the price decreases by that much per. Right. So this was in dollars and this was in miles. Right. So per 1,000 miles, 1,000 miles. Looks like I wrote mics. I also could have gotten this out of the 1,000 piece. That means it's right decreasing by $1,836 per 1,000 miles. Right. So that's what that means on average. For every 1,000 miles. No, that can't be right. Is it? Aha. I was off by a decimal. Dun, dun, dun. All right. That means it decreases by point. Man, how embarrassing. 1,836 or $183.60. My bad, friends. My apologies to you. Look at, I'll erase that decimal point and I'll draw in a prettier one. The best decimal point you've ever seen. Right there. So yeah, there we go. That makes more sense. I just didn't read my decimal place right. And yeah, and then by translating by 1,000, that means I was going to shift the decimal place 3 places, 1, 2, 3, which is why I got $183.60. Right. So every 1,000 miles more on a car, it decreases in that amount. What does the y-intercept mean? What does this y-intercept mean? That would be the price when what? What is 0? 0 what? No, you might have been right. I don't think I heard. Yeah, the mileage is 0. That means the average price was $19,000. All right, so that was, yeah, $19,720 is the average price for, right, 0 miles. Now, it said that these were all used cars, so used cars usually have miles on them. People don't usually buy cars just to, like, look at them and not drive them. It's possible. Yeah, maybe. So notice none of the cars were even close to that. The car with the least miles on it had 8,000 miles on it. Right? So they were all used some amount. But this is what the predicted starting cost would have been. All right, how about this? Approximate the the mileage of an automobile that costs that much money. So if that's the predicted value, 15,500, graphically speaking, actually I could even, let's show you this graphically. If I write y equals 15,500, oh wait, I've got to write that in terms of thousands, so that's going to be 15.5. There we go. Graphically speaking, I would be looking for what does the purple line's x coordinate equal, okay, when y is 15.5. And that's what we end up seeing. So I would expect that it has about 22.96 or 22,000 miles on it. Would be a car that's around $15,500. Algebraically, how could I do that? What I could do is plug in 15,500 for y and solve for x, negative 0.1836x plus 19.72. Right, so if I plug this in for y, I can solve for x. How could I solve that for x? Even though these are weird numbers, we'll use a calculator. How do I get rid of this? Or what should I get rid of first? This is being multiplied, being added. When solving, we SADMAP, gentlemen. So we will subtract from both sides. Also, oh dear! Guys, I just made the mistake again. Because my axes were in thousands, this is actually 15.5. Not my bad. So subtract, there we go. Now it's not lined up, but that's fine. 19.72 from that. I'm going to reach for a calculator. 15.5 minus 19.72. That sounds negative to me. I get... Nope, I just wrote it wrong, guys. Man, I'm off my game. Negative 4.22 equals negative 0.1836 x. How do I get rid of that number in front of the x? Yeah, divide. Does anyone know what I'm expecting this to be? Let's see, 4.22 divided by 0.1836. The number's on the screen already. Not quite the same number, oddly enough. Oh, because I truncated some of my decimals. But nonetheless, right, if I wanted to predict it, I could plug this in for y and solve for the corresponding x. So if I had this much money to spend, I should expect that the car that I buy would have around 22,000 miles on it. What if I ask the other way around? What if I want to know what would the price be for a car that has 6,000 miles on it? What would I do? Where would I put that 6,000? Well, 6,000 is in miles, and that's the x-axis. And watch, I can actually type it in here. I'll write x equals, instead of 6,000, it's just going to be 6. Right? Because the mileage was already in thousands. And I would be interested in what is the y value when x is that? And so this would be my answer. What is my answer graphically? And what does that 18.6 mean? That's the price. Does that mean it's $18? $18,000. That's quite a bit more money, actually. I don't think I want to buy that car. No, thank you. So let's. If I was to do it algebraically, this is what it would look like. This will be the last thing I do. This video's taken some time, but we're refreshing our minds since coming back from vacation. I would have plugged in 6 for x, and then like this. This doesn't even need algebra. This is now just arithmetic. I would have done 6 times that. 6 times negative 0.18. Nope, I typed it wrong. Man, I can't even like type in a calculator these days. It's been so long since I've been teaching math class. This I get negative 1.1016. What do I expect these numbers to add to be? One's negative. 18.6184. Where have we seen that before? Right there. Bam. All right, so here's graphically how you could predict, and here's algebraically how you could predict. That's as far as we'll get today. Thanks for watching, internet friends. Adios.